Hey everyone, and welcome to The Explainer. Today, we're diving deep into a technique that's like the bedrock of competitive programming, complete search. And yeah, it might sound simple, but trust me, understanding it is the key to cracking some seriously complex problems. Let's get right into it.
All right, I've got a question for you. Seriously, think about this for a sec. You're in an exam, or maybe an interview, staring at a tough problem. You're drawing a total blank on some super clever, optimized solution. What's your ultimate safety net? What's the one thing you can fall back on that will almost always work?
Well, that's safety net. It's complete search. Think of it as the brute force powerhouse of your algorithm toolkit. The idea is shockingly simple, really. You just generate every single possible solution, check each one against the rules, and then pick the best one. It's your guaranteed path to a correct answer, as long as you've got the time to let it do its thing. All right, so here's the game plan for today. We're going to start with the absolute fundamentals, generating things like subsets and permutations. From there, we'll level up to a more intelligent kind of search called backtracking, and we'll use the classic n-queens problem to see how it works. Then, we'll learn how to seriously speed things up with pruning and a cool trick called meet in the middle. And finally, we'll wrap it all up with a solid revision strategy so you can lock this all in. Okay, first things first, we have to master generating subsets. This is one of those foundational patterns. It shows up everywhere. The question is, if you're given a bunch of items, how do you systematically create every single possible combination of them?
So there are basically two classic ways to pull this off, and they each have their own pros and cons. The first is an elegant recursive search, which is really intuitive. The second is a super clever and wicked fast technique using something called bit representation. Let's break them both down.
All right, so this recursive method, it's all about making choices. Picture this. You're walking through your list of items one by one. For each item, you hit a fork in the road. You have two choices. Choice 1, you don't include the item in your current subset. That's the first recursive call you see, search k plus 1. Choice 2, you do include it. You push it onto your list, and then you make the next recursive call. This branching, this series of choices, is what explores every single possibility.
Now pay attention here, because this is probably the most common mistake I see. That subset pop backline, it is absolutely mission critical. This is what we call backtracking. After you go down a path where you've included an item, you have to undo that choice. You have to pop it back off. If you forget, your state gets messed up, and every future subset will have that leftover item in it. So the golden rule is always clean up your state after a recursive call.
Okay, now for method 2. And honestly, this one is just brilliant. If you have n items, you have exactly 2 to the power of n possible subsets. Well, it just so happens that there are also 2 to the n integers from 0 all the way up to 2 to the n minus 1. The trick is to map every one of those numbers to a unique subset. But how? You look at its binary form. If the ith bit is a 1, you include the ith element in your set. So a number like 11001 in binary means you take items 0, 3, and 4. It's unbelievably fast and super clean to write. So, the big question, which one you actually use in an exam? Well, it really comes down to a trade-off. Recursion is more intuitive for sure, and it's way more flexible if you need to add complex rules. But if you're just after raw speed, the bitmask is king. No contest. When you just need to generate all the subsets fast, the iterative bitmask is usually the way to go.
Awesome. So we've got subsets down. That's where order doesn't matter. Now let's switch gears and tackle permutations, where the whole point is the ordering of the elements. The good news is, the recursive game plan for permutations is almost the same as for subsets, with just one key twist. See, we can't reuse items, so we gotta keep track of what we've already picked. The easiest way is with a simple Boolean array. Let's call it chosen. Before you add an item, you check, is it chosen? If not, you mark it as chosen, add it, and make your recursive call. And, you guessed it, the most important part is backtracking. When that call returns, you unmark it as chosen, freeing it up for other paths to use.
Okay, we've built the foundation. Now it's time to level up from just generating stuff to a much smarter kind of complete search called backtracking. And there's no better example to learn this than the classic, the famous n-queens problem.
So what exactly is backtracking? You can think of it as a smarter, more efficient recursive search. Instead of blindly generating every single possibility, you build your solution one step at a time. And at each step, you check, is this path still valid? If it's not, if you've already broken a rule, you stop. You immediately abandon that path and go back. It's kind of like you're in a maze.
Instead of exploring every single path to the very end, the moment you hit a wall, you immediately turn back and try another way.
So here's the puzzle. Place n queens on an n by n chessboard so that no two queens are attacking each other. That means no two can be in the same row, same column, or on the same diagonal. Now, the key insight here, the thing that makes this solvable, is to simplify our search. We're going to decide to place exactly one queen per row. That takes care of the row constraint automatically. All we have to worry about now are the columns and diagonals.
And this is where the code gets really clever. To check if a square is safe in constant time, O of 1, we use a few simple helper arrays, one for columns and one for each of the two types of diagonals. You can identify any diagonal by the sum of the coordinates, x plus y, or their difference, x minus y. That one little if statement you see there does all the heavy lifting. It lets us check instantly if placing a queen is a valid move before we even try. It's incredibly efficient.
So backtracking is already a massive improvement over basic brute force. But we can do even better. We can get even more aggressive about cutting off those dead-end branches. This is called pruning the search. And the effect? Well, it can be absolutely mind-blowing. To really see pruning in action, let's look at a different problem. The challenge is to find every possible path on a 7x7 grid that starts at the top left, ends at the bottom right, and visits every single square exactly once. Writing a basic backtracking solution for this is pretty straightforward, but its performance is, let's just say it's not great.
Okay, get ready for this. Just look at the insane impact of a few simple, clever observations. The basic naive algorithm, 483 seconds, and it makes 76 billion recursive calls. That is just bonkers. Now look at step 3, wall splitting. The idea is simple. If our current path ever traps some unvisited squares behind a wall so they can't be reached, we know it's a dead end. That one check takes our runtime from over 100 seconds down to 1.8 seconds. Boom. A couple more tweaks and we're under a second. That's the power of pruning. We're talking about a nearly 1,000 times speed up. And as the source for this explainer points out, this is a usual phenomenon. This isn't some weird one-off thing. Because these search trees grow exponentially, finding one smart rule to prune a branch high up can eliminate billions of useless calculations down the line.
So pruning is all about making our search smarter. But what if we could just make the problem we're searching smaller in the first place? Well, that's the whole idea behind our next technique, meet in the middle.
This technique is just amazing for a certain class of problems, like the famous subset sum problem. Instead of doing one massive search on n items, you split them into two smaller groups of n over 2. You do a complete search on the first half and store all the possible results. Then you do a search on the second half, and here's the magic. You then efficiently combine the results from the two halves. What this does is it turns an O of 2 to the n complexity into O of 2 to the n times over 2, which, trust me, is a colossal improvement. For something like n equals 40, that's literally the difference between the code finishing in a few minutes versus running for a few years.
All right, we have covered a ton of ground, from the absolute basics of generation to these super advanced optimization tricks. So let's boil this all down into a clear, step-by-step strategy you can actually use when you face one of these problems.
Here it is, your 5-step thinking process. Step 1, always check the constraints. If n is something small, like 20 or less, a complete search is probably feasible. Step 2, decide how you're going to generate all the possible states. Recursion? Bit masks? Step 3, build your core backtracking logic. Step 4, and this is the big one, actively hunt for ways to prune the search. Literally ask yourself, how can I make this fail faster? And finally, step 5, ask yourself if the problem has a structure where you could maybe split it in half and use meet in the middle.
So you see, complete search, when you combine it with smart backtracking and pruning, it's not just some dumb brute force method at all. It's a flexible, powerful, and absolutely essential problem-solving tool. So I'll leave you with this question. Now that you've got this entire toolkit, what's that one unsolvable problem that you're going to go try and crack first? Thanks for tuning in.